Yeah, and I can get started. So this is the ACE tutorial. So today I will present a new functions to PyHealth. So previously all we have presented are related to electronic health record analysis and modeling. And today I'm going to introduce the biosignal modeling part, which is newly added to this package. Although it's not in the current pip install PyHealth and PyPy version, but it's already in the repo. We're gonna comprehensively test it and then upload to be a new version for PyHealth. And so this is a development team, and gradually we will add more people in. I think Benjamin next time we also a member of it. And yeah, and I am Chao Qiang. I'm a PhD student in UIUC, and yeah, today I will present. I'll be the presenter, and then during my presentation, if you are interested in our package, just search PyHealth in Google, and you will find our webpage. And also definitely check out our recorded previous live video session and at this AI for Health YouTube channel. So yeah, this is as usual, we will first present our development team, and yeah, this basically are the current development team, and we also wanted to send an acknowledgement to these to other members. So today we are going to introduce our biosignal modeling pipeline. So before doing that, I wanted to go over the 5-stage machine learning pipeline. This whole concept framework in PyHealth, we model the pipeline uniformly into these 5 stages. The first stage is data processing. Second stage, healthcare task definition. Third stage to select the model, and then train the model and do the evaluation or the inference on top of the best model. So each of the step is handled by a single module. So next is our main topic. I'm going to show you the machine learning pipeline for electronic health record data and for the biosignal data. So for the left-hand side, this is a complete pipeline for drug recommendation on mimic3 dataset using the transformer model. And on the right-hand side is the newly added sleep staging task on the open sleep EDF data with our control WR encoder. So this is a paper we have written a while ago, and I borrowed the encoder of the module inside to be a supervised model here. So the left-hand side is the EHR pipeline, right-hand side is biosignal pipeline, and different box basically are the modules in the pipeline. So we can have like a one-by-one comparison. You will see that the API doesn't change at all. And yeah, so that's basically the advantage of these new features. You can use a new feature input, but the API doesn't change.
Chelsea, are you going to go through both sides in detail? It would be good to, even for the previous one, drug recommendation, just quickly go through that.
Yeah, I will going to show the differences actually, like the internal differences between these two pipelines. So first, for the EHR pipeline, I'm going to discuss the input and output for this module. So the first box is basically the module input, nothing like special. So for the EHR pipeline, this part is basically doing data set loading. And then the second part, and as we mentioned before, is step 2 is to set a machine learning healthcare task on top of the data set. Then we define, in step 3, we are going to define a model and then to train the model and then do the evaluation. As suggested by these module names and the argument names, it's pretty clear like how to use these APIs and then what are the functions of them. And so the thing I want to discuss here is the input and output of the EHR pipeline. So when you want to, if you wanted to use our pipeline, you probably in front of you, you probably have a list of these CSV files, this medical like a medical database as a folder in front of you, and then you probably will use our mimic3 dataset, this and data loader API to want to process this folder of CSV files. And what internally what we do is we will load these folders from the disk and then parallelly process each of the patient and then clean them into this multi-level tree structure. And then right now the data is is stored in the memory. The data, I mean this base underscore data set, these an object. And then for the second step, healthcare dataset dot set task. For this part, what we do internally is we will operate directly in the memory. We will clean up the patient from this multi-level tree structure to this kind of sample-based structure, which will be ready for the data loaders to load and then combine to a data batch so that it can be used for the deep learning model training. This is the I/O for electronic health record pipeline. But when I was implementing the same pipeline for signal data, one obvious problem is that the signal data originally is super large in the disk. For example, the signal data are usually stored in a lot of different files as this one. And so basically I can give you some background of the signal data. If this is a like EEG signal, that means the patient will wear some measurable devices around his head, and then different like touched points will collect one signal, and then a lot of these touch points will have one by one, they have like a lot of signals recorded simultaneously. So this EEG signal is basically a multi-channel signal. And here each signal is stored in this PSG file. And there is another associated file, it's called hypnogram. This is the annotation files for this EEG data. So if you wanted to process the data, these two files has to go together, the PSG file and the hypnogram file. And for other data set, they probably have different ways to store the data set, but usually they will store different recordings separately in different files, just like this. And this EEG or ECG data, they are super large in disk. For example, here, it might be 500 gigabytes. We cannot directly load them into the memory. And in our implementation, what we do is that we only store the signal path, which is the absolute path in this machine, to this hierarchical structure. This is like basically the first step. We extract the path from the disk to the memory, but we doesn't process the data directly. And then for the second step, which is a set task step, we again define a task as we do in electronic health record pipeline. We define a task and then we process based on this signal path. It's a little bit complicated. What we do is we use the signal path to process a super long recording, and we split the recordings into different segments. For example, for EEG sleep staging task, we will segment a long recording, like 10 hours recording, into 30 seconds, 30 seconds, 30 seconds. Each 30 seconds will be the feature input to the model, and then there will be one labels associated with each 30-second segment. So this is what we do in the memory. We use a signal path, and then we load the whole very long recording into the memory, and then we split this very long recording segment by segment, and then we store it back to the disk.
So
right now,
can I ask a clarification question? Where did you specify those 30-second interval? Like, is there some configuration file you have to specify?
For that part of information, we encoded that in this task function. So the task function will define what the task looks like. For example, in here, our task is to use the machine learning model to label a 30-second signal. But we can also define it in different ways. We can also
I see. So you will show that task staging that function later, or?
Yeah, I can show that later. But yeah, I can show that later definitely. But this staging function, basically, we transform a super long recording into a multiple 30-second like segment, and each segment will itself be a machine learning sample.
And you will write those 30-second interval into a separate file back to the.
Yeah, I will write it into a separate file and back to the disk.
Okay. And
And this
assume,
is the
the folder,
classical.
output folder, all those things will be specified in somewhere in your function as well.
Yeah, it
Like-
will be specified somewhere. It's the same as EHR model. For EHR model, we will load this like hierarchical structure into a cache file, and then this cache path is computed by our program. And here we will compute a cache file for this sample as a sample folder, and then we store this 30-second signals separately as a separate files into that cache folder. This is a standard practice in the biosignal processing pipeline. And what we do is that we still want to.
Question.
Go ahead.
So there's some limitation, I guess, how many files you can store in a folder, right? I think in Linux there's like 26 or 200,000 or something. Potentially there will be many small files, right?
Oh yes, but I remember when I was doing doing a previous project, I stored 17 million samples out to a folder.
The same folder, one folder?
Yeah, the same folder, one folder.
Maybe.
It doesn't cause an issue to me.
Okay.
Yeah, I think when I was checking other GitHub repo on similar problem setting, they all do the same thing. Yeah, another way to, if you want to store into fewer sample files, is that you can store the data batch by batch, not a single samples, but like 256 samples together as one single file. That's also possible. Yeah. So so I will maybe go back to the EHR pipeline. In EHR pipeline, in this part, we will
Can I
get
ask you
the
a question?
samples. Sure. Yeah. Go ahead.
How do you in the epochs, can you tie them at the end back to the patient? So you load, also you split this entire signal up, the EEG data.
Yeah.
Then you process them and then you store them back in the cache.
Yeah.
But do you introduce an index so that you know from which patient?
Oh yeah. That's the problem. Yeah, that's the part I want to introduce later. Like right now.
Okay, sorry.
Actually, yeah.
Okay.
I mean, in the EEG pipeline, what we do is we store these samples out as a complete samples, and this sample already contains all the information related to the features and the labels. But here we can't do that because the samples, collectively, if we store all the samples into the memory, it's still super large. So we write the samples out, but we store the path of the samples inside of this JSON structure. We know the patient ID, the record ID. We can also add the segment ID, like which position of the long recording this sample is previously. And then we have a path here. So this is the samples we dump out. But this sample is not ready for machine learning models to train on because it only has other meta level information. It doesn't contain any signal information. So in our data loader, it has additional function, but user don't need to specify that because we already encode into it. So the data loaders here, it will according to the sample path to load the samples from that folder. And then to replace this path, use the actual samples to replace the path to be a complete sample. I will show a demos for this part.
Here, Chaoqi, this particular record you're showing there, this correspond to 1/32.
Yeah, correspond to 1/32. And then there is an absolute path to that sample.
And for example, you have this patient ID, right? I assume the record ID is which segment for this patient?
Right now, the record ID is one patient might have different recordings. One patient probably will record for 3 days. Each day will have a long recording. Right now, this record ID refer to that index. We didn't store the segment ID here right now, but it's easy to store it. Right now, our task is we treat each 30-second epoch as an independent epoch. We didn't consider their time order information.
it may be down the road useful.
Yeah, it's easy to add back to this like JSON.
But of course,
Yeah, down the road it will be useful.
yeah, I think that's
Yeah.
that's
Yeah, this is just a vague like sketch of how we implement this, but I'm going to show you a demo and about a complete biosignal pipeline, and then show you some internal data changes and the I/O information to help you understand like how we handle these large EEG data sets, how we communicate between the memory and the disk. And yeah, for the rest of the pipeline are the same as the EHR. And if you only want to use our APIs, then you won't feel any difference. But internally, we do have like different implementation.
so. Chachi, one question on the data loader part for test data. I mean, for evaluation, you need their ground truth label, right? But for
yeah, I need the ground truth label.
deployed in some live system where you will not have labels. So do we handle those use cases, or that this part is more for model training? And
this part is for model training. For model testing, we can have a JSON files without these label attributes.
So I'm just saying, for when you do the data loader part, maybe we don't have that logic in this particular pipeline, but I imagine the test data loader or would not have those hypnogram, right? Those hypnogram are the labels, and in this particular,
yes.
But in the when you deploy this for inference, those samples will not have those labels.
Yeah, for inference, this hypnogram.edf files doesn't exist. And this hypnogram, only this label and key is connected to this hypnogram. If we don't have this hypnogram file, we will not have a label key here in this JSON.
Okay, so we can
we can still load it. We can still load it. The other attribute won't be affected.
Okay.
Yeah, I'm going.
The other part, this is very easy to add, but probably necessary for real application. That is like the timestamp of those samples, right? When you split this recording, I assume in the EDF file, don't they have some timestamp?
I think the timestamp will be similar to the segment ID in that long recording.
Right. So there's some logic you have to provide, right, to figure out.
Yeah.
You make a prediction, right? This is awake, right? Then you should tell the. I mean, one thing is what George asked, right? Can we associate with the original patient? Yes. Then we should also associate with the timestamp, right? At this time interval, this is the stage of the sleep.
Oh yeah. So yeah, I think everything will be very clear when I show the pipelines like step by step.
So the label you said it's associated with the hypnogram.
Yeah,
is it part of that file, or where are these labels stored?
Yeah, it's part of the file. So these PSG files, it only provide the signal itself, no labels. And this hypnogram only provide us with the label information, no signal.
Okay, and is this the same standard Mass General is using and Brandon is using?
Sorry, say it again.
Is that standard here? What you are showing, is this how Brandon is using and presenting the data?
Maybe it probably is different, because right now what I'm showing is called Sleep EDF. It's a open data set, and everybody can log in. It's open access.
How many channels? Remember, is like a.
So this Sleep EDF it has two portions. One portion is this portion, and one portion is telemetry portion. And for the first portion, it has 7 channels. For the second portion, it has just 5 channels, I remember.
Okay.
So these two are like 2 different studies conducted on different time range.
We cannot merge them, right? This is like a very
we cannot merge them, but they probably have some overlapping channels. They have like detailed descriptions for the channels.
So when you do this, you take one of this data set, right? One study.
Yeah, I take one of them, but the APIs is the same for them. They have the same format, only different number of channels.
The other question I have is when you do the split, right? You can split by patient, right? I mean,
Yeah, I split by patient into the training, validation, and the test set.
Because when I see this, it's hard to tell how you specify. Oh, you said split by patient. So that function itself has some logic. When you
Yeah. Our function has some logic. We can split by patient ID, or we can also split by record ID, which will scatter this same data from one patient to training, validation, and test. But we didn't do that. We split by patient.
Okay.
Yeah. So I can show you the pipeline, and it's related to PyHealth. We have a website. We have a GitHub repo. We are actively maintaining this GitHub repo, and this semester we are going to add other modalities to PyHealth. Right now, we support electronic health record data. We support biosignal data. We are going to support these image format data like chest and X-ray, and the clinical notes or other clinical reports data.
Cool.
And
So,
we
okay, go ahead.
Go ahead.
Finish.
We are also actively asking for external contributors to help us to collectively build this package. And then we have like PyHealth live video channels ready, and other different tutorials for each of the specific functions in the PyHealth. Then that's basically it. Thanks very much.
Thanks, Chelsea. This is very helpful. It takes a pretty long time, but I think it's very helpful for explaining all the concept and a lot of details. So maybe you can